Hello Abaqus user, welcome to Abaqus Acumen for quick and sound learning. Today's session we are going to do on a nonlinear buckling. So on my screen what you're seeing is a hollow 50 millimeter by 50 millimeter, 2 millimeter in thickness and 300 millimeter in height column get buckle, and this exercise is to calculate what is the buckling load for the structure. Now in this particular model we have included the imperfection. Now for the imperfection we first done a linear buckling and get those imperfection into here. So in terms of learning, you'll understand the whole procedure how to do a nonlinear buckling. You'll also understand how to bring an imperfection in the model. Now why imperfection is required? In real structure, if somebody say it is a column, it is not a perfect column. It will have some imperfection, it will be tilted some here and there. So once you bring an imperfection in a model, a buckling model, you get a more realistic number. So that will be the learning from this part along with a nonlinear buckling procedure. So this is we are going to do the today's exercise. Also, in case you want to go through the basics of the buckling theory, we also have a video, our video on the Abaqus linear buckling analysis finite element method. You can go through this video and go through the theory in case you want to go through the theory part. Now let's go through the brief PowerPoint presentation to understand what we are going to do. So today's session will be a nonlinear buckling in Abaqus standard. This will be an implicit solver we want to do in Abaqus standard. Now how to do a buckling in Abaqus standard? There are a standard format. So in that standard format, what we are going to do, first we are going to build a model. So once we build a model, we are going to do a linear buckling. So this will be give eigenvalue and eigenmode. So it is going to give a bifurcation point, what is the maximum linear buckling load. It will be overestimated most of the time because it's just a linear buckling mode. In reality the buckling load will be lower than this linear buckling. But to just get a first estimation on the buckling load, we have to do a linear buckling. In this linear buckling, we are going to do a perturbation step called linear star buckling. We are asking for 3 number of mode, and then you have the various iteration what we are going to use. In this file, we'll add this particular command node file u comma just to get a displacement in the field file. And the output what we are going to get eigenvalue and the mode and deformation pattern in node field file. So based on this first analysis we are going to do nonlinear buckling. So we get eigenvalue, what is a bifurcation load that we are going to apply it. And then to get imperfection model we are going to use this eigenmode. This in node field displacement file we are going to call. We are going to use star imperfection file comma whatever linear buckling file name and the step, and then we'll put imperfection for 3 more. So you can have 5, 6, 10 whatever the number of imperfection eigenmode what you want. And then we are going to capture the post buckling behavior. So to get a post buckling behavior in Abaqus you have arc line method, and we are going to use the Rix method. So this will be the learning part. Along with imperfection you have this snap through behavior and the Rix method. Now what is a snap through behavior? So the first problem is like this column buckling. The similar problem we are going to do, and then you have can crush. So in this once you do a linear buckling, it just overestimate, it give a bifurcation point based on this just a linear force versus displacement. In the reality the limiting load or nonlinear buckling is quite lower. So after once the structure is buckled, it is very difficult to capture. So we are going to capture this snap through behavior using arc line method or the Rix method. So you see once it go through the snap through behavior, then once it is buckled the parts get in contact, and then it can go to the load start getting increased. So let's go to the problem now. It will be typical aluminum properties. 50 by 50 by 300 millimeter 2 millimeter thick. It will be fixed pin condition. bottom will be fixed, at the top it will be pin. And on my screen what you are seeing is the two picture is for linear buckling and the other is for non-linear buckling. The unit which we are going to use, turn, millimeter, Newton and second. And just on the linear buckling side, we are going to use a star buckle. You have two different solver which Abaqus offer. Lancos is a faster and for large number of hygiene modes. Subscribe is a faster with a few modes. You can use star C load, D load, temperature, only elastic property because it's just the protrusion step, and no hybrid or the contact element. So let's start with the problem. So let me clear this and set the directory. So I set the directory. Now what we are going to do, first we'll quickly create column. It will be 3D deformable shell extrusion. So I'm going to model on, I just put 0 0 as a center point. I'm going to put 49 by 49. Now why 49 by 49 point I'm taking? Because I am putting the structure on the mid surface. So I'll show you how we get where we can give propose mid, outer or the top. So right now I'm putting on the mid structure. So we quickly done that. Then we'll extrude this by 300. So we done that. Now we'll create the property. Now for linear buckling we just required a elastic property. So I'm going to stick to just a modulus and the Poisson's ratio. I'm not going to put a plasticity data. So we done that. I'll create a thickness. It will be 2 millimeter. So we put 2 and we are going to assign this property to this column. And then you see here shell offset definition, it's a mid surface. So we are seeing it's mid surface. You can say top surface or bottom surface. So we selected is a we define it as a mid surface. Now we'll quickly create a instant. So we create column and then we'll go to the meshing part. Now meshing we cannot do in assembly, it has to do in part. We are going to use a particular sweep algorithm. So we are going to use sweep algorithm that is good for this type of structure. We'll quickly assign S for R, that's what actually we assign. Now seed we are going to use for 5. Now for linear buckling you can have coarse mesh because you just want to capture the stiffness, geometrical stiffness of the part. But since we are going to use this imperfection going to bring into nonlinear model, so we are going to use a 5. So I'm going with a global size 5 and then I'll just mesh it. So we done got a good structural mesh. Then we'll create the top and the bottom node set, because we are going to put one reference point, and that reference point we are going to, that rigid reference point we are going to tie this node. So it will be easy for us to put a boundary condition and load, and then that will be easy for capturing what is a buckling load getting in terms of the unit load what we are going to apply. So let's create a node set. So top, let me check, we have selected everything. So we have selected, done. Bottom, so we've done a meshing. We also created the two node set. Now I'm going to use some constraint here. I'm going to put some reference point and going to tie the periphery node to the reference point, so it will be easy to put boundary condition and load. So I'm going to create the two reference points, so I just put here one will be at 0, 0, that will be on the one end, and the other will be 0, 0, 300, so this will be on this side. Now we quickly create constraint, so I say bottom and I'm going to put rigid body, continue. I'm going to put a tie. Once I put tie, you go to the arrow and select the bottom, you select and then select a reference point, so that I'm going to select the reference point 1 and say okay. So this is the first constraint we have created with respect to reference point. I will create one more. I say top, rigid body, continue, tie, and then you are going to select the top, and then you are going to select the top reference point. So this way we have created the part. Now we quickly created a boundary condition, so let's create a boundary condition. So boundary condition, create, it will be bottom, it will be end caster condition, end caster, so we put that, and the top we are going to constraint x and y, it's only vertical movement we are allowing, so we created top, so 1 and 2 we are going to put. Now we'll create a step, it will be linear buckling, and it will be like a linear protrusion step. So buckling, we are going to say we are going to use subspace, we are going to do for 3, and we are going with a high number of iteration, because sometime the number of iteration are lower, it throw out that the iteration is lower. So just for safer side, I just add 1 0, but it will be too high, it can be 100 is also fine for this. So we created that. Now we'll quickly apply unit load. So in the linear buckling, you are going to apply it 1 Newton minus 1 direction. So negative Z, we are going to apply this load. So we have done this. Now let me save this file as a linear buckling. Let me create a job. We put a data check. So let's check if there is any error in terms of preprocessor related. If there is no preprocessor error, then we can. So it's done, there is no issue. Now just important point here, guys, once we build this, we have to put this node file u comma. So we are going to create a node file, one fill file, which we are going to use for call for this imperfection. It will have a displacement. So this is we are going to add this. Now this you can add from here. You go to the edit keyboard in model, and then you can go at the bottom and you can add here. I generally prefer to generally do it using keyword file. So I just open a file in using keypad, so I just open it and then I put control and I'm going to add here the node file command. So I just copy here the node space fill and then U is a displacement. That's what actually we are going to do. So I paste it here and I'm going to submit using command prompt. So Abaqus 615j is equal to linear, so that file we are going to run. So let's wait for getting results for this linear buckling mode. So analysis is done. So let's check how the results looks like. So now this is, you see what you are seeing is the first buckling mode, and we applied a 1 unit load 1 Newton. So one that applied unit load multiply by 97152. So this is the 97,152 is the first buckling mode, and this is the buckling deformation shape for the first mode. So the hygiene mode is this deformed shape, and this is the load. Now second one is 1 e power 05 Newton. Third is 1.2 e power 05. So these are the three different mode. So it's all nodal displacement. So this displacement we are going to use for imperfection. We are not going to give this high displacement, but the some factor of that we are going to do in use in imperfection. And the load for nonlinear buckling we are going to apply this around 97 or 1 e power 05. So around 10,000 Newton is a good number to apply to get what is a realistic buckling load. So now let's close this ODB. So we don't want this. So let's open the same 5 linear buckling. Now this file only we are going to improve. Now we are done all modeling, so first we'll go and we are going to delete this step. So we don't want this step. Now for the geometric model everything is there, which I just deleted the step because we are going to use a nonlinear buckling. Now the important thing is property side, you have to edit it. You just have a modulus, Young's modulus and Poisson's ratio. So we are going to add the plasticity data. So it will be like 160 will be the yield, 340 will be at 30% strain. So that's what actually we added. Let me check the loads. We have both boundary condition here. Now what we are going to do, we are going to create a non-linear buckling. Now we are not going to create a load, we are going to create a step. The step name will be, you can give non-linear buckling. It will be static rigs, NL jump on. We are not going to use the maximum load proportionality factor or stopping criteria. We are not going to use. It will be initial, it will be 0.01. 1.0 maximum. What we are going to do, this is just to calculate what is, and then 1000 will be the good enough to get this. So get this maximum from 100 to 1000 because it take a lot of step in risk method. So we done that, we created the risk method, use risk method. Now I'll apply load. Now load I'm going to apply is minus 10,000 because that is what estimation we got from the linear buckling. Now for non-linear buckling it will be on a lower side, but we just get a first number is around 10,000. It was 90, no, it was almost I have to add one more zero, so it is 100k is the Newton is the number, so we apply that. Now we'll create a job, non-linear buckling. Let's go to data check. So data check is a good option to check if you have any pre-processor related issue. Now the while the preprocessor is done, so it is done. Now for this, now we done a first step, we created the field file. Now we use a risk method to calculate what is a snap through behavior. For that we are using this. Now we have to add the imperfection in the model. Now how to add this? Again, you can go here, model, keyword, and just before the steps you can add this imperfection in the model. I generally prefer using a text pad. So I'm going to this non-linear, so control N. So we applied this 100k Newton. Load, we have used risk method, we have used some 0.001 as this the starting point. We have end caster condition, we have non-linearity. Now I'll just add the imperfection here. Now I just copied it for saving a time. Now this is very important step in the non-linear buckling. Now you give a star imperfection comma file. Now this file is a linear buckling file. That's what actually I have to copy here. So it's a linear buckling. So you can see there is a field file generated here, node buckling field. So that's what the particular file we are going to call linear underscore buckling step 1. So in that file we have all the displacement. So for the first mode deformation, we are going to multiply by some factor. Now why it is 0.2 not 1 or 10? So our thickness is 2 millimeter. So 1/10 of the thickness for the first mode, 0.2. Second mode is half of the first one. Third mode is half of the second one. Now this particular imperfection, this imperfection sensitivity you have to calculate. Now this is just an example problem, but in when you do actual research or actual your project work with your professor, or you have to calculate this imperfection sensitivity, you have to calculate, you have to change this parameter for the different combination of hygiene mode, because once you start doing during the buckling, it is not going to, the first mode is going to influence, but there is also contribution from second, third, fourth, fifth. This is example problem, so we have taken a 3, but you can go till 6, and then you have to do a imperfection sensitivity study. So now what I am taken is thickness divided by 10, 1/10 of the thickness, and then second mode imperfection is taken half of the first one. and third one is the half of the second one. That's what actually we are done. So let me run this using command prompt. So I'm going to say abq614 j is equal to, I'm going to take this nonlinear buckling. CPUs I'm going to use 2 and then interactive 1 abq6145. So I missed the I just put 614, it will be 6145. So paste CPUs is equal to 2 and then interactive. So it's just started. Let's see on the preprocess side. So it's a preprocess started. It gone to standard.exe. So just wait for the results, and once results are out, then we can discuss. Now guys, I just terminated the run because it was going through all the arcline method and it was going through snap through viewer. We are not interested to do that right now, so let's check the results. So let me put a viewport annotation fix, and then let's set 18. Let me also put this back 1 minute. So legend, we are going to set it for the state also. So you are seeing the results on my screen. So we are just checking. So we don't have contact. So because of this imperfection on the deformation IGN mode, it is start getting buckling. So it is structures get buckle, and if you define a contact, then you can define a contact, and with the same arc line you can have fold generated. Now we can do in the next video to do that, to capture a detailed post buckling behavior. So now what you see is the buckling deformation mode. Now what is a buckling load, how to calculate that? So we'll quickly go through that. Now we'll go to history output. So you go to the history output, and then you select in history output load proportionality factor for the whole model. So once you plot that, so this is exactly your load. So your load is somewhere around 85. That is what exactly is the load where actually it get buckled. So we put 100k, so it's around 85 90. That particular load, it is just getting buckled. Now we can get that load by, you can see how the stress is generated, and then wherever it get buckle, it start the getting stress. So in this particular model we are not define contact. If you are define contact, then you can put this arc line and see what particular snap through behavior. Now what particularly, I'll just go back for one more time for the load proportionality factor. Now this is what snap through behavior. If you define a contact, then it will start pulling back up again. So just going through this, so we are just captured somewhere here, but if you put a contact, then it can go down and start picking up. It once it get in contact, you get again stiffness, and then it's move up. Now what is that load? We'll just quickly check. We'll put a reaction force on. So now you see there is 51. So let me go back. Now if we start from 0, it will say your load is getting increased. So it gone to 89, and then it start reducing. So this is the around 89 K is our buckling load. So through linear buckling we got around 98K, so this is almost 10% lower. Now one more caution. Now the imperfection in the model, we are just put some 1/10 of thickness for the first mode, and then for second mode and third mode we put half of the first and then half of the second. But we have to do a detailed study on the imperfection, so you have to do a detailed study in terms of imperfection sensitivity, and then you can see how much is this load again for experimental data and then your simulation data. So this is, then you see after that it's just load reduced, so the structure get buckle. So this was just a brief video on the nonlinear buckling which was pending from our side for the long time. Thanks a lot for watching this. If you like this video, don't forget to like us or subscribe us. Thank you. Bye bye.